asks specifically about hybridization on the central atom. And again, we're going to follow the process. So draw the best Lewis structure. From there, you're going to count the electron groups. And once you know electron groups, it will tell you hybridization, so geometry. And now seems like a good point to say, you may have noticed that I only ask you about electron geometry. There's this thing called molecular geometry, and other professors and other Gen Chem classes will ask about molecular geometry. I do not, so heads up. All you have to know is the electron geometries for this course. And so electron geometry, so I will not ask molecular geometry. And molecular geometries are in your textbook. And but I just choose not to go there. We've got enough other things to do, and I'll be happy if you can go, tell me the electron geometry. Of course, hybridization is the other one, the second one, and bond angles are the third thing that you can tell. So now, and this question doesn't say it, all it says is what is the hybridization of the central atom in SF5 minus? There is a minus sign in there. Our process is going to be to draw the best Lewis structure. So I have 6 valence electrons for sulfur. I have 5 times 7 for fluorine, and then I add 1 more. That's going to be 35, 36, and 6 is 42. That's a lot of valence electrons. But it's the same process. Take your S, put it in the middle. It is less electronegative. Surround it by all of your fluorines. It doesn't matter where you put your fluorines right now because this is a Lewis structure, and Lewis structures are allowed to show shape, but they don't have to. What they do have to show is all 42 of these glorious electrons. So far I have 10 showing, and 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, squeeze them in there, 38, 40, again I'll make those a little darker because they're hard to see up there. And now I just got to 40, and all my fluorines have octets, and so my last 2 do go on the sulfur atom, which means that our central sulfur atom has 6 electron groups. That means there must be 6 orbitals hybridized. So sp would have 2 hybridized orbitals. On the other end, sp3 is 4, d2 is 6. 6 hybridized orbitals will be sp3d2. And let's see, we have hybridization, electron geometry. Does anybody remember what the electron geometry is if there are 6 electron groups?
Octahedral.
Thank you, Daryl. Octahedral. And in octahedral, each of the angles is 90 degrees if there are no pairs of or lone pairs of electrons. So whenever there's a pair of electrons, we just write less than, whatever that perfect bond angle is. So this is less than 90 degrees. Not that anybody was asking, but that we will. Any questions about this number 1 here? For number 2, we have bromine trifluoride. For this, there's going to be 7 plus 3 times 7, which equals 4 times 7, or 28 electrons. put them in. I got my single bonds to my 3 fluorines have used 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now I have nothing to do except I've only got 24 electrons in here. I have 4 more to put in. 26, 28. And in this case, I have 1, 2, 3, 4, 5 electron groups. Which means I must have 5 hybridized orbitals. And 5 hybridized orbitals would be sp3d. But we can say more than that. Does anybody else, not Daryl, but somebody else, remember the name of the electron geometry when you have 5 electron groups? It's a little trickier, or it's certainly the longest name.
Trigonal Bipyramidal.
You got it. Thank you, Selden. Trigonal Bipyramidal. And trigonal bipyramidal is the trickiest one as far as bond angles goes, because the bond angles are 90 and 120 degrees. And I'll draw it in just a second here. But I want to note that a couple things. So whenever there's a pair of electrons, those are going to make those bond angles less than. And we're actually going to draw this and see what happens. So bromine in its geometry, or sorry, we'll call it, typically I call this the shape, draw the shape. So bromine, there are 5 positions. There are 3 axial positions, 3 equatorial positions and 2 axial. And so the axial positions are straight up and straight down. I typically draw one out to the left, and then the ones, on the right. Then the ones on the left are going to be an out wedge and a back wedge. Those are the 5 positions for a bromine, for a trigonal bipyramidal electron geometry. Now, as you put in, and we'll start by putting in the electron pairs. So electron pairs go to the equatorial positions. Sorry, I'm covering that up as I write it. Electron pairs go to the equatorial positions. And the equatorial positions can be thought of as the equator or the middle of the molecule. So again, it's not technically correct to draw bonds here, but the idea is that these 2 pairs of electrons are in these positions. So you could either just draw the pairs of electrons here, or I'm okay if you draw the bonds. And the 3 fluorines go in the other 3 positions. Now, the reason that the electrons go in these 2 positions, which this reason is hard for me to see in general, but an equatorial position is on average farther away from all of its neighbors. So here's the statement: electron pairs go to the equatorial positions, and then to continue that, because equatorial positions are on average farther away from their neighbors. Because equatorial positions are on average farther away from, I guess I put neighbors there, but neighbors means other positions. So if I were to put a pair of electrons here, it would have 3 other groups at 90 degrees to it. Whereas here, it has 90, 120, 120, and 90. And so, again, I'd have to think more about that. But the electron pairs go to the equatorial positions. Any questions about what I've drawn?